we could probably have got by just fine without ever going into space. You know, we've learned a lot of stuff, but in terms of eating and sleeping and procreating and all those things, we were doing a pretty good job of it before we went into space. We went into space because we're curious. And here are a couple of quotes that I really like. You know, one by Goethe, one by Robert H. Goddard. Now, Robert H. Goddard was the American who actually did a little calculations about what it takes to go to the moon. And here he was a professor, a teacher, and here he is giving a lecture about the problems encountered and the energies that were required to get a payload, hopefully carrying a human to the moon. Now that was his dream. And he actually got some money from the federal government and some from private foundations to pursue his dream of building rockets that were practical. And I just love this picture of him in his blockhouse, getting ready to watch this rocket takes off. And here was his transportation system to get the rocket to the pad. Just an amazing thing, and yet he proved many of the technologies necessary to do liquid fuel engines. And so the military, of course, found out about liquid fuel engines. And so the Germans went to work during World War II and developed them as military hardware. And we captured some of them, brought them over here, and took them down to White Sands. And this is a wonderful old movie of one of the very first flights that carried a camera that looked back at Earth. And those of you that are approaching as old as I was and that I am, and used to go to the movies, you remember the Movie-Town News and the voice of the guy that narrated Movie-Town News. Well, you will recognize it on this wonderful video. The beginning of space exploration.
Flying laboratory is recovered by Clyde Holliday of Johns Hopkins, who prepared it for its trip to the upper stratosphere. Rivaling the fantastic imagination of Jules Verne, the camera brought back a record of a flight into the heavens of a captured German V-2 rocket. At White Sands, New Mexico, the huge missile takes off. Air Force pictures show the rocket in flight, and the flying camera automatically takes over. The huge projectile drops the Earth behind at the tremendous speed of 4,000 feet per second. The rotation of the rocket causes the planet to spin before the lens, and the camera photographs the Earth 65 miles straight down. The horizon, 720 miles away, and the curvature of the Earth are astonishingly apparent in this still picture from the film. An observer in the rocket could have seen San Diego, Salt Lake City, Kansas City, and San Antonio. Approximately 1,600,000 square miles of the Earth's surface was revealed. The rocket reached the 65-mile height in 3 minutes. This giant engine of destruction, designed by Hitler to annihilate allied nations, now serves the worthy cause of peacetime research.
Flying those V-2s was before my time, of course, but it was particularly interesting because they didn't have effective range safety in those days. And I think it was the second one that they launched went off and headed towards El Paso, which would have been bad press if it had launched. So they had problems with these early V-2s, but one of the later ones, I think it was after this one, the Naval Research Laboratory guys were interested in what comes out of the sun that causes the Earth to have an ionosphere, an ionized layer, which permits long-distance radio communication by VHF. And so there was an argument about, is it X-rays, is it ultraviolet light, what does it? And so one of the very earliest solar space experiments was very simple. They took a little piece of film and they put it behind a thin window of beryllium. X-rays penetrate beryllium, but ultraviolet light can't. fired up in this rocket, and the rocket tumbled around and landed, and they were able to recover their little camera and developed it, and the film was darkened, which says that the sun was emitting X-rays. Well, I've made my living for the last 30 years studying the X-ray emission of the sun, and that was the very first measurement of it on a German V2. But the space research never really got much traction in the 50s. It wasn't until the Russians started flying things and we realized that we were falling behind that the space program of the United States of America really took off, and we began to develop our own rockets. And of course, the famous speech given here at Rice is considered
the exploration of space will go ahead, whether we join in it or not. And it is one of the great adventures of all time. And no nation which expects to be the leader of other nations can expect to stay behind. But why, some say, the moon? Why choose this as our goal? And they may well ask, why climb the highest mountain? Why, 35 years ago, fly the Atlantic? Why does Rice play Texas? We choose to go to the moon. We choose to go to the moon. We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard. For I think we're going to do it. And I think that we must pay what needs to be paid. But it will be done. And it will be done before the end of this decade. And I am delighted that this university is playing a part in putting a man on the moon as part of a great national effort of the United States of America.
Pretty audacious things they were going to do. You know, we'd never flown anybody in space. We'd barely flown very many experiments in space. We didn't have any of the rockets or infrastructure or the knowledge to know how to do that. But by George, you know, that was a good speech. That was a darn good speech. And that speech was not given without a considerable amount of thought in advance and looking at what the possibilities were. And that speech had the advantage of a competitor. And the United States of America understands competition. And so there we go. We went to the moon. There's Buzz Aldrin, Apollo 11, setting out scientific instruments on the moon, some of which are still returning scientific data. Now, we didn't go to the moon to do science, but science certainly profited from the Apollo program. We went to the moon to show we could do it, learn how, and establish our kind of society as a stronger, more competent, better society than the other guys. So there was Buzz Aldrin doing his thing. Here, one flight later is Al Bean. We'll hear about Al Bean in the next picture. But this spacecraft here, I believe, was called Surveyor. And it was sent out in advance to land on the moon and get a feel for what it was made of, because people didn't know whether it was going to just be dust and you'd disappear, or whether it was rock, or what was the nature of the moon. So they set up this guy here, and it had a little scoop, and it dug a trench, and we're still doing that. You know, we just sent one to Mars a couple of years ago that landed in the polar regions and reached out with a scoop and dug a trench, and found water, found ice, water, ice. Well, we didn't find anything in the moon, but after this surveyor had been on the moon for quite a little while, we sent Al Bean out, and these guys went down and they brought some pieces back. This is the scoop here. From the surveyor, they took pieces off, brought them home, and was able to learn a great deal about the effect of long-term exposure to space on materials, was able to learn about the nature of the high-energy particles that bombard the surface of the moon from the sun. This was a good piece of engineering and a good piece of science. And there's the trip home right back there. and had to walk over this time, but later on we had a buggy. Now this is a kind of a fun picture. On the right is a picture painted by that same Al Bean of an experiment that was done on Apollo 15. Very important experiment to prove whether or not Galileo was right. Galileo was the first guy that recognized that if you didn't have air resistance, a light thing would fall just the same speed as a heavy thing. And the story goes that he dropped a big ball and a little ball from the Leaning Tower of Pisa to see whether they got to the Earth at the same time. But if you really want to test this, you want to drop a hammer and a feather. So Dave Scott took this falcon feather, and this was one of their hammers that they used for their geologic work. And here he's standing, and so we'll see if Galileo was right. By George, it looks like he was. Now that's a good experiment. You know, we don't have absolute timing on that, but first order, Galileo was right, and it only cost us a few billion dollars. Okay, as the program proceeded, we got this fun rover, and so this is the rover Grand Prix at Apollo 16, and that rock that was out in front was Galileo.
You're okay on one graduate, I have a shot again. On the LSD? Yep. Okay. Working.
Working in 1/6 gravity isn't totally trivial.
Hey, Griffith. Flight plans can you have Jack Bush speakers up there while I should go. I think it's too bad. Hey, whatever. You're saying they can back the arrangement and understood clock time. Yeah. It's better than the trail. Right, they say clock time Go fine. You copy what I'm saying? Yes, I did. Is that something you guys have done down here? No.
So anyway, we did get there. We got there in time, and unfortunately we didn't have a plan other than to get to the moon and do some stuff. And so a lot of the investment of getting up there sort of dissipated afterwards because the nation hadn't really decided where to go from here. And this has been one of the issues with the space program, with the human space program. The robotic space program, which we'll talk about in a little while, is percolated along in a pretty orderly way. But the human space program really needs a mission. It really needs an objective that is difficult and that's way off there and that's going to pay off a lot for the human spirit. We always try to sell the human space program based on science and based on material advantage and you'll live longer and things, but basically we fly humans up there because we're humans. And it just isn't the same to put a robotic measuring system on top of Mount Everest as it is for a person to go up there and do it. And of course you learn a lot in doing it, and it has a lot of payoffs. But we basically do it because we're human, because we're curious. So what's the next thing to do? What's the next thing to do? Well, we build a shuttle. And the shuttle is the most amazing and competent spacecraft that I think will ever be built. It could carry big loads into space. It could bring big loads back. And it was a very good working environment while you're up there, and I got to fly on it. So on July 29th, 1985, here we go. We had a launch attempt 17 days earlier that got within 3 seconds, but there was a problem with the valve and we had shut down, and so the astronauts got to go to the post-launch parties, which was fun, but we really would have rather been in space. We came back 17 days later and we got off the pad. And let me tell you, that is shake, rattle, and roll. That's really, really great. For the first 2 minutes, the solids are burning and it's really loud and noisy and shaky, and then it's like electric drive. The liquid engines are so smooth. So my job up there was primarily to operate the 4 solar telescopes, which were on the instrument pointing system in the payload bay of the shuttle. My partner, Carl Hennig, was in charge of operating the Space Lab systems. My job was running these 4 solar telescopes. And once you got an experiment kicked off, you can watch the Earth go by below. And it was an amazing experience. And our data were really good. We brought back excellent data. We won the Spaceflight Achievement Award that year. But you know, humans operating remote sensing instruments are really a problem. You got to keep them alive. They move around, they wiggle things. And so we don't do this kind of experiment on the human missions anymore. We do these with robotic instruments. One of the most important things that you can study that requires humans is studying living things in space, is studying humans. And so that's one of the big things that justifies, you know, putting people up there nowadays. And anyway, I got to take that ride, and I forgot to tell you that on the second try, we got off the pad all right within the last 10 minutes of a 4-hour window, and about 5 minutes out, one of our main engines shut down. So we had the only engine shut down on the way to orbit, but fortunately, we were close enough that we could get into orbit with the remaining 2, and we were on our way. Okay, after the use of the space shuttle in this sorting mode to carry instruments up to work from the space shuttle as a platform, the decision was made that we're going to have a space station, International Space Station. And it is an awesome, awesome outfit, but the way you get to it, up until the middle of next year when we're going to quit flying shuttles anymore, was on the shuttle. Same shuttle life, or same kind of vehicle life.
How was that, man? What a ride.
Now, after the Challenger accident, we've gotten a lot more careful about shuttles. And so now, you go up there to the ISS, and before you dock, you've got to do one of these turnaround deals so you can see if all your tiles are all right, everything is okay. So there's the docking. Going up. Pretty tricky. You know, fly up there and these 2 things are, and make them match. But it works. Worked pretty reliably.
And for almost all of us on board Atlantis, we've been here before, but it's bigger than we remember, and speaking for myself, better than I remember. I love this place.
4 batteries, safety S-can.
I think for our entire time frame here, we were a 12-person crew that operated together. But this one is to friends we're going to leave behind, and new friends that we've made, close friends, my friends. We've had a great time together. We're going to close the hatch shortly, and we're going to depart. And of course, as always, it'll be a little bit sad. But we'll see you all on the surface of planet Earth again soon.
You know, that is a remarkable device to have built in space. And it wasn't done, you know, just with a bunch of people working secretly somewhere. It was done with full public disclosure. It involved lots and lots of different nations. You know, we're working with our former enemies. The space program has done a lot of good things. A lot of things that are way better than building tanks and missiles to shoot at each other. So there is, thankfully, another way to get into space, and that's on the Soyuz. Totally different kind of rocket. Remarkably reliable and robust system with a remarkably efficient way of getting the thing integrated and out on the pad and fired up. And of course, I have to show you the fun things of weightlessness. I love this one. You know, the whole science part of the inside of the International Space Station is in these big modules. You don't handle those suckers up there as going in, of course, to play baseball or soccer. You've got your plant growth experiments, and you got to clean the house. Well, this is a big house. Now, when you go up on the Soyuz, you come back this way. No landing on a runway. Just at this point, they fire rockets, and they give you about a 10, 15 G kick in the pants. If everything works fine, you're home safe and sound. And it's good we have the cooperation with the Russians, because we've decided not to send our spacecraft there anymore for a while. Now I want to give you a tour of this enormous big home in space.
Here we go.
This is Butch Wilmore, and this was made a year or two ago after the Space Lab, after the ISS was finally finished. You know, this thing takes about 5 minutes to run. It's a big house. Now, as you watch this, conceive of the problems of how to find something.
Russian segment. Set up the gear, the computers, cameras on the walls. We'll continue forward now. Our next stop will be the first juncture in the Russian segment, where we'll look down first into the docking compartment. And you see a progress cargo transfer there at the bottom. If you look up now, you'll see the brand new Russian segment, the MRM-2, the science module. Got a little bit of gear packed in it for the transit uphill, and they're starting to put it into work now. We're going to turn around, just taking the lead, and we're in the FGB. A lot of cargo stored in the FGB.
So you see stuff stowed everywhere. So the housekeeping and the tracking and the operation of such a
A lot of
hotel.
stuff. There's food,
Amazing
storage,
challenge.
some scientific material, stuff behind the walls, of course, stuff on the floor here. Little mirror here, place where you can clean up, take a bath. And now we're in the next juncture where we look down into the other Soyuz that is attached. It's a very juncture between the FGB and Node 1. Just backing up now into Node 1. Through some more storage area in this PMA-1, this mating adapter. Now we open up into Node 1. You see Roman here. He's working on A-Red. And we'll turn around the other way. You see Randy, Bobby, and Mike working, doing some EMU freak things. Continuing into the lab. Say hi, Frank. Hello, is that Commander? How's this, Commander? Frank DeWitt. Robotics workstations. See, this basically a bicycle. Station hiding. Coming on through. Well, there's Bob first. In the flesh. Sitting here in Node 2. Coming up Node 2, of course, a connection for various parts of the station. We'll look this way into Columbus. You can see the station spacewalking suits, the EMUs, are stashed there on the ceiling. Some more storage on the floor. Japanese experimental module, the GEM. With another sleep station on the floor, other things stored here and there. A working laboratory. Come on, we're into the shuttle now, through the primary veining adapter.
Now we're entering the space shuttle. Now we're getting in territory I'm familiar with.
Making the 90-degree turn.
I hope none of you get airsick by this picture.
Now we're on the mid-deck. There's our commander. Charlie, hold on. Search. And now we're continuing up to the flight deck. See the flight deck? Commander seat, pilot seat. We've got a couple of seats removed here in the back that we'll have for entry. And then we'll look out the overhead window at station. We certainly hope you've enjoyed your tour from Soyuz to shuttle. Thanks for all the great work everybody's doing on the ground supporting us. Thank you.
Workout time.
This is a beautiful fly around after the shuttle undocked before people went home. They did a whole circuit out of the space station, taking videos the whole time from the shuttle. Took about an hour and a half, which is as long as it takes to get around the Earth on time. And I look at these and I think, boy, isn't it neat to be alive when people know how to do this stuff? You know, we don't exactly know how the pyramids were built. We got a pretty good idea how the cathedrals were built. But to be able to marshal people's brains and people's industrial capacity and people's ability to pay taxes and then spend them on something and end up with a gadget like this in orbit around the Earth kind of is magic in my view. And I think it gives great hope for the future. Because maybe a species that's able to get off of the very risky high point of having nuclear missiles pointed at each other and work together, build a thing like this, that's good. That's good. Now, where are we going to go from here? You know, what's the role of humans in space? You know, the Chinese have decided they want some humans in space, and the Indians are thinking about it, and we've been doing it, and the Russians know how to do it, and what's our future role? And I worry, frankly, that we don't have a well-defined strategic plan about how we're going to spend all this taxpayers' money to give us the kind of bang for the buck that, for instance, the Apollo program did. You know, the Apollo program had a whole large fraction of all the people on the planet watch it. You know, the big accomplishment of our society is that it was done publicly. You know, we stood right out there in front, and when the rockets blew up, we were all watching. But I really hope that before too long, we'll get together and we'll put together a real long-term vision that lets you budget properly and plan properly, and so the young folks have got something to look forward to that want to be astronauts. So we'll experience this sort of thing. Well, there's a lot more to space exploration than putting people up there. We found that for many, many applications, we've got good enough robots now that we're better off to put robots up there. And when I say robots, I mean telescopes or any of the remotely operated tools that we have. And this program has paid big dividends in all these fields. And I'm going to talk about a couple of these things, but the last bullet, I want you to particularly notice. Because as far as I'm concerned, one of the reasons that the Cold War did not end up as a nuclear war is that because of space intelligence spying systems, each side knew a whole lot about what the other side was doing. They had good, reliable data on a lot of things, and one of the big issues is making a mistake based on bad information. So I think this is an important thing. You know, space surveillance in this day and age is an important thing. Well, let's talk about a few of the things that we have done robotically. We all watch the Weather Channel, and we've got these spacecraft up there now, paid for with taxpayer dollars, that have improved our ability to do weather forecast enormously. And they're also used for all kinds of other important global-wide monitoring activities. And I just love this picture taken fairly recently by GLOW 13 of the Western Hemisphere, top to bottom. Just as an example of the kind of robotic capability that we have now. You know, that spacecraft that took that picture is 24,000 miles out there. It's out there far enough that its orbital period is 24 hours. So it just stays in the same place over there, and which makes it a great place to monitor the weather from. So I won't go more into Earth remote sensing. I won't go more into high resolution photography, but you can all go to Google Earth and see a picture of your house taken from space. And do it. It's a lot of fun. You know, there you are, right there. You know, if you got somebody aiming a missile at you, maybe you don't like that data out there, but it's out there. Now, I don't want to just talk about the U.S. program. The Japanese have a really vigorous program of robotic space exploration. And they've just returned a sample of dirt from an asteroid. Took them 7 years to get out there and get it back. This is an asteroid Itokawa. This is an artist's conception about how the spacecraft touched down gently and brought home some dirt. This is an image of asteroid Itokawa taken by this mission named Hayabusa. And this is a pretty small hunk of rock, half a kilometer. And this is a comparison size of the International Space Station. And what they call this is an orbiting rubble pile. You know, the question is, why is it even hanging together at all? Because based on having visited it, it seems like there isn't a lot of rock there. And of course, being such a small thing, it doesn't have a lot of gravity. But there it is. And it has been visited. And stuff was brought back on this thing. This is how the re-entry, they came down in Australia. And before they ever opened up the canisters, and here's one of the canisters, they did an MRI on them, and there wasn't anything in there. Big disappointment. You know, they expected to see some rocks or dirt or something. But they did finally open up one of them. I don't think the second one has been opened yet. And they found that on the walls of the container was dust. And it was dust from that asteroid. And so they did scrape the sample off with this little piece of Teflon. And then they did very, very careful analysis. And they said, well, this is from the spacecraft, but this chunk of olivine is actually from Itokawa. And then this is aluminum, and that's aluminum, and this chunk of pyroxene is from Itokawa. And they got enough data to know that this is definitely not Earth contamination. This is real asteroid stuff. And so we're not the only ones that are doing fun things scientifically in space. Now I want to talk about a mission called Deep impact epoxy, which sent a spacecraft off to a comet or an asteroid a number of years ago, and crashed the gadget into it and took a picture of the ejecta and learned a considerable amount about the properties of that particular object. But then they sent Deep Impact off to look at comets. And they got within 500 miles of Comet Hartley 2 last November. And this is a picture of the comet as you would see it from the Earth through a telescope. And right here in the center is the hard part, and there it is. And it's got a snowstorm around it. There's water, ice, snowflakes around this comet. Nobody expected that. And some of these are big as a basketball. Nobody expected that. Well, here's how they think it works. The center of that comet down below is frozen CO2, dry ice, and that sublimes away and leaks out, and they see these jets coming out of that comet, and they figure that the jets are picking up water, ice, and making a snowstorm around this comet. So that's another one of the fun, very recent results from space exploration. Now I want to talk a little about my rocket. I'm a solar astronomer, and we recently launched a mission called the Solar Dynamics Observer. And this is a picture of the sun in 3 colors. The blue is iron in the state that corresponds to about 800,000 degrees. The green about 1.3 million, the red about 2 million. You take pictures and put them together, and you get a feeling of what the temperature is like in the sun's corona. It's hotter here, it's cooler here, cool. And so we know a lot about the sun observationally. And one thing about the sun, being a nearby star, we can take pictures like this, which are tremendously detailed and show these explosive events, these amazing outpouring of energy in sufficient detail that makes lots of interesting problems for theorists like David Alexander and folks here at Rice, who have to try to explain how nature does it. And we've always wanted to get a 3D picture of the ejectas which come from these big solar storms, because when those are called coronal mass ejections, when they get to the Earth, they compress our magnetic field and they cause all kinds of interesting effects. And so we would like to be able to predict it better because they're technologically dangerous. And so we flew a couple of spacecraft called Stereo, and these were launched at the same time, and one drifts away from the Earth in one direction, the other drifts away from the Earth in the other direction, and so they give you a stereoscopic view of the sun. And this is a composite picture which shows the surface of the sun, shows the near corona, it shows a coronal mass ejection heading out into space, and now we can get a feel for what the shape of those guys are. Here's the sun, and every once in a while you see a little flash, and there goes the coronal mass ejection, and it goes out. And these pictures here are actually looking at an enormous volume of space from quite near the sun to out beyond the Earth's orbit. So we can track these ejections when they happen, and we can attempt to understand what are the forces that cause them to move the way they move, and why do they evolve the way they do. And so here's some Irish colleagues have done some theoretical work and some modeling. This is based on the data from the Stereo spacecraft, and there you see a coronal mass ejection coming out. And you may have noticed that when it started, it was all above the plane of the planets. But now 20 solar, 30 solar radii out, it is equally up and down. So it started out this way, and it turned back down. And so this says that a lot more of these are going to strike the Earth than you might think, given the direction that they're launched. And somebody's figured out why, and so now we have a better ability to make the predictions. I just showed this to emphasize that space exploration, a lot of it's done in the computer. You know, we now have computer power that lets us deal with these masses of data and build theoretical models which can describe what nature's doing. Okay, now let's go back to this one. Okay, this, here's your lecture. You're going to be tested on this afterwards. There is a picture of a solar active region made with this SDO mission I told you about, the Solar Dynamics Orbiter with the 3 different colors. Okay? We're going to concentrate on that hunk here. Now that hunk has been observed at the same time by a bunch of other missions, by a Japanese mission called Hinode in 1 wavelength. On Hinode is another instrument that observes in the ultraviolet. These instruments together can tell us about the motion of material in the sun's atmosphere. These instruments on the Solar Dynamics Orbiter are just pictures, and they can show us the moving stuff in different colors. This is the 1 point, this is about 40,000 degrees, this is about 800,000 degrees, this is about 1.5 million degrees. And so now we have the ability in our computers and in our minds to put together information from a lot of different perspectives. And that's what it takes to do solar physics. Now, here is that little piece of the sun that I just showed you in the preceding picture. This piece right here. Come on, Loren, get it right. Okay, these are movies. And this one is at 40,000 degrees, and you see these little red flashes. This one is at 800,000 degrees. This one is 1.5 million degrees. And what you see is little red flashes all over this gadget. No, let's back up. Come on, Loren, get it right. And so the conclusion from these experiments is that these little ejectors, which are called rapid blue-shifted events, stuff squirting out of the surface of the sun up through the chromosphere into the corona, have an important role to play in building up the supply of material in the corona that can then be ejected off towards the Earth and cause things like you see here in this cartoon. A coronal mass ejection comes off to the Earth, mashes into the magnetosphere, causes magnetic storms. And now, because we've got the good computers, we've got good data, we've got good theory, we can make pictures like this one that for some reason isn't running. Let's try again. There we go. Whoop. Well, if you could have seen it, then it did work this afternoon. Oh, it's working up here. Okay. This is a computer model made by the Space Plasma Physics Group at the University of Maryland of an event that happened in 1997. And out here you have the data from the spacecraft. This is the ram pressure of the wind blowing out to the Earth. This is the direction of the magnetic field measured by the spacecraft. And all of the stuff you see here is done in the computers. We've got the measurement of the idea of the density. whereas the blue is low density and the red is high density. We got a prediction of what the aurora should look like in the northern latitudes. And so you see that the sun really jerks our magnetic field around when these winds blow by. Okay, we will close by going to the edge of the universe. Here's a Hubble ultra deep field picture. And many of these galaxies, and this is almost all galaxies, this is just a little tiny piece of the sky in the northern hemisphere, about 1/5 the size of the moon. So this is just a tiny piece of sky. Not 1/5, this is 1 arc minute, yeah. Anyway, zillions of galaxies go back way to the time of the Big Bang. The Big Bang was about 13.75 million years ago. Billion years ago. And after the, well, let's just take a look. Let's look at the timeline. There you go. There's the Big Bang. And things expanded very rapidly during this inflation period. Later on, we could see the planets and the galaxies start to form. The question is why? You know, what is the thing that makes these concentrations of mass happen? I'll tell you. Because if the gases produced in the Big Bang are strictly uniform, there's no differential in gravity anywhere, and so you shouldn't get stars, you shouldn't get galaxies. Well, the pictures that you just saw go back here quite near the Big Bang, 13/14 of the way back. But what was it like before they formed? Well, we can learn this by looking at the cosmic microwave background. Now, this was discovered back in 1978 and resulted in a couple of 8 Bell Labs, AT&T investigators, and they were interested in radio issues, and they had this big microwave dish, and they kept getting this noise no matter where they pointed it. And they thought the pigeons' droppings were doing it, or they had a lot of problems trying to figure it out. Finally, they realized that what they were seeing was microwaves from the cosmos. And that was the discovery of the cosmic microwave background. Now, this had been predicted before this time by Gamow and a couple other guys. They said if there was a Big Bang, then there should have been radiation from that Big Bang. And over the zillions of years since that time, this radiation would have cooled. So it started out being exceedingly hot, but by now it should be about 3 degrees absolute, if it could be fine. Well, it's hard to see radiation from something that cold, but in microwaves you can do it, and that's what these fellows were seeing. And indeed, when we had better measurements and we made a spectrum, this spectrum matches what's called a black body at 2.725 plus or minus 0.001 degrees absolute. So the Big Bang all at once became more than just a theory. We had seen something that had been predicted that must be the relic after effects of the Big Bang. Now, this is very uniform across the sky, within about 0.004. But if you go and look really carefully, you get pictures like this. This was made by the Cosmic Background Explorer of around 1992 timeframe. And what you see when you look in the sky are differences in temperature. Very, very tiny differences in temperature, about 0.0005 absolute. But there are differences in temperature. The background isn't uniform. The background has structure. And then we flew another probe in 2001 with much better angular resolution. You see the same structures, but with much better angular resolution. And we see from these little clumps that for some reason After the Big Bang, the gases weren't uniform. There were variations in density, and that's why we had the formation of galaxies and the universe as we know it. Now, why does it look that way? Think of it this way. If you are on the ground and you're looking up at the bottom of a cloud, what you're seeing is light, which is scattered along, and the light which enters your eye was the one that scattered last on the bottom of the cloud. Okay, if you're looking back in time, and the Big Bang is sending out light, and it's scattering here, and then it exits the scattering medium, the thing that you see is the pattern on the sky at the last scattering of that light, just like the light coming through the cloud. And so from this amazing thing, we have been able to learn some remarkable results. I don't pretend to understand this, folks. I'm spinning you a yarn. There are people that do, because you can't draw these remarkable conclusions just from the data. You've got to have a theory which ties it together, and you've got to have a lot of colleagues which criticize your theory and make you prove it. But here's what we think this story is. First of all, I told you that there were variations in the temperature of the cosmic microwave background of about 0.004. Well, that is because the solar system is moving with respect to the overall galaxy. And so you look one direction, it's a little bit blue because of Doppler effects. You look the other direction, and it's a little bit red from the light that's coming from the direction you went. And so that says that we are moving through the universe at about 358 kilometers a second. Well, that's something you really need to know. I mean, if you're going to cook breakfast tomorrow morning, how could you do it without knowing that? But you can remove this dipole effect, this velocity thing, and then you get the maps that I showed you, which, if you're smart enough, can tell you that the age of the universe is precisely 13.75 billion years old, and that it is made up of things that we didn't even know about before these pictures were made. Namely, the universe that we've been studying so carefully, the ordinary matter is about 4% of the stuff. About 23% of it is stuff which is like matter, but which we can't see. And that had been thought about before, because people have looked at the movement of stars and galaxies, and they see that the stars are moving in a way that implies that there's more material, there's more mass in that galaxy than we can see by counting stars. So there must be some dark matter. So we kind of thought that there was some dark matter. But 73% of the stuff is something called dark energy, which we don't have a clue what it is. But it is something which is causing the expansion of our universe to accelerate. It's spreading out faster now than it was day before yesterday, a little bit. This is probably the cosmological, astronomical, astrophysical question of the age. What is dark energy? So there's things for graduate students to do, even in the future. Okay, that's the end of the talk. We're back home. Thank you very much.
Stuff there. There are times. There's time for some questions. If anyone has questions back here, we think. By the way, Loren, what's your? I guess don't be shy, folks.
Thanks a lot, Dr. Acton. I was wondering what your personal opinion is, and you told us a little bit about it earlier, on what the benefits are of human exploration going to Mars as opposed to robotic exploration, and what it'll take to get us there.
I think, and I'm a bit of a Philistine on this, I think the benefit of going to Mars is in figuring out how to do it, and in the fact that everybody is going to be really interested. The rovers we've sent there have just returned wonderful stuff, probably better stuff than the astronauts will do, scientifically. But there's more to it than just science. And when I see the light in the eyes of the little kids when I go into schools and talk about space flight and space exploration, I say, you know, every penny that we've spent is worth it, because those little kids are interested in it, and it's exciting to them. And I know that's maybe a difficult point of view to sell, but that's mine. I think it's worth it because we can afford it, and let's do it, because we'll learn a whole bunch going there, and it sure will be fun watching the television. Like John F. Kennedy said, we choose to go to the moon. We choose to go to the moon. Not because it's easy, but because it's hard. And I think that speaks to the human spirit in an important way, and it isn't as if we can't afford it. It's a pretty small part of the international.
I'd like to follow up on the Mars exploration thing with a different viewpoint question. Houston Chronicle, I guess a month or so ago, published a report that a couple of scientists, the British astronomer Royal and the Australian researcher that read the planet of smallpox, but primarily was important than that. Both of them thinking that humans will be extinct in 100 years. And here in the United States, the director of NASA's Institute for Space Studies says if we go ahead and burn all the feasibly available fossil fuels, including tar sands and oil shales, we'll tip the planet into the same transition that Venus went through, effectively sterilizing the place. So the follow-up question related to the Mars exploration, where are we about the possibility of getting self-sustainable human settlements somewhere else as a survival issue?
Well, again, I'm giving you the gospel according to Loren. I don't think it makes a bit of sense to establish a colony of Homo sapiens on any of the planets that are reachable. Requires resources which those planets just don't have. Even if we send, you know, all the necessary stuff in advance, it's not going to be a self-sustaining deal, at least not for very many people. And we have the advantage here on Earth of a magnetic field and an atmosphere which protects us from the hazards of being exposed to space. Cosmic rays are pretty much directed other ways, and the ultraviolet light gets stopped by the ozone. So it's a nicely tuned system. You know, we're designed to live on this planet. We're not designed to live on any other we know about. And so I frankly think that's just blowing smoke. If we're going to survive as a species, we're going to have to do it here. And that's not going to last for too long. You know, about 10 billion years, the sun's going to turn into a red giant, and that's Katie bar the door. That's the end of the earth. I don't think I'm going to live to see it. You know?